And the final talk of this session is on the exciting topic of getting the formal semantics from executable implementations. And Jiangyi from University of Wisconsin-Madison will be giving the talk. On to you.
Hi everyone, I'm Jiangyi, and I'm a second-year PhD student from University of Wisconsin-Madison. Today I will be presenting the paper Synthesizing Formal Semantics from the Executable Interpreters. We all know that formal semantics are great, and they can be used under many different circumstances. They can be used for verification, they are very useful for synthesis, and they can also be applied in static analysis. But there is still one big issue. They are too hard to be written for engineers. In fact, it is very rare that the program semantics are being actively designed by people outside the PL academia, and our tool comes for the rescue. It automatically synthesizes all this formal semantics given only the interpreter. So how does our tool work? To introduce that, let's just start with all the three example terms within the IMP language. We've got a atom term 1, we've got the plus sign, and we've also got the do while statements. So how do we create their semantics? The key idea is we use everything that is already available to us. We know that we know what symbols are allowed in the semantics, and we can write it down as a grammar, which is the syntax of semantics here. And we all know that there will be an interpreter that exists for the given language. The interpreter itself is capable of running any program under any input, and it just provides the output in return. Can we synthesize the semantics with only those alone? So let's think of the easiest way to do that. To generate many examples from the interpreter, and then synthesize the whole semantics with them. So here's the interpreter, which we already have. And we've got a bunch of example inputs and the programs. So why don't we try to create a single semantics automatically that works for all these three terms? To achieve that, we tried to invoke an off-the-shelf solver, and then we failed. The solver just ran forever because the whole semantic function is too hard to synthesize in one shot. So what are the lessons we learned from this? To begin with, blindly generating all these examples doesn't help much in covering the full language. And the full semantic function is too big. So we shouldn't synthesize all the whole function at once. Instead, we should synthesize one for each of the term types and then put those together. And this naturally leads to our solution to the problem, synthesizing rule by rule. And this is actually our key approach. For the semantic function, which you can see in the green box, instead of synthesizing all those things, everything at once, we break it up and synthesize one rule at a time. So we can see the semantic function for IMP is broken into many rules, and there's one rule for each of the syntax constructs. So we've got one rule for assign, we've got another semantic rule for if then else, and another for the for loop. And here's our next observation. To introduce that, let's first have a look at the semantic rules for each of the three terms. So for the atom term 1, we can see there's only one output, O equals to 1. And for the later ones, we can see although there are a lot of premises in each of the each of the semantic rules, they still share a lot of parts. And there are many parts that looks alike, which are the ones colored in blue. And those are the structural parts that are automatically deducted from the syntax, because we assume that the parent semantics, which is the parts under the line, it's always using the semantics of the child terms. And given all those semantic parts in blue, we don't need to spend time synthesizing them, and they will automatically go into the rule template here. So what are the rule templates? They're just used to put together what we already have, which are the structural parts, with what we will try to get, which are the red parts. we've already got the structural parts, and there are still some undefined parts in the semantic rule templates, which are colored in red. And those things are called the hosts. So what are the hosts? The hosts are just the first order logic functions that will become our synthesis target. In the whole process of doing the synthesis, we will only care about synthesizing the hosts themselves. And the structural parts are already given to us for free. And let's just here's our approach, just condensed into a flowchart. We first start by breaking down the rules into a bunch of rule templates, and then we will use the example inputs, example outputs, and the programs to help with the synthesis of all these hosts within each of the rule template. The example input programs and outputs just come directly from the interpreter. After the synthesis, a candidate rule will be obtained and passed into the verifier. The verifier will test if the generated candidate semantic rule is truly correct, which means it's just doing the same thing as the interpreter, or if there's some discrepancy in the rule, which means the rule should be synthesized once another time to see if we can get a correct one. We'll then introduce the technical problem here we encountered by going through 3 examples. Let's start with the simplest. Getting the semantics of the atom term 1. So the language here is still the IMP, but we are only using one variable as its state. Here, the input state I is just a single integer representing what was the value before the whole execution. And the output will be another int, but it means the evaluation results of the single term. So the term is number 1, and we all know that whatever the input is, the output should be O equals to 1. And we have the F here, which is the whole we mentioned in earlier slides. The F stands for the whole function that relates the inputs to the outputs. And it is actually the only thing we are going to synthesize here for this rule template to get a complete semantic rule. So why don't we see how we synthesize F? To do so, we first extract all these examples from the interpreter, and as I've just mentioned, whatever the input value takes, the output is always 1. And we also know what is allowed in the semantics, written as the syntax of the semantic functions. And given all this information, we can then transform this into a syntax-guided synthesis problem. And there are a lot of off-the-shelf tools available. The answer is F equals to 1, and that's what we would expect. So why don't we come to a more difficult case? So for this case, it is more realistic because we're trying to synthesize the semantics of a non-leaf node. And the techniques for this case can be generalized to arbitrary non-recursive syntactical constructs. The parts in the green rectangle are automatically got from the syntax, because for non-leaves, the semantic function call to child terms are always needed because the parent semantics make use of them. Again, the F here is the whole that characterizes how the output is gathered from all those child terms. But here, we have 2 more hosts, the G and H. So what are they? They are the hosts for data flow. Those functions show how the inputs to the child semantics come from the input of the parent term, which is the I here. Given the child semantics here in the semantic rule, the next question would be how to express them. The child semantics may not be synthesized yet. It may use other types of unseen syntactical constructs, or even worse, it may use another plus sign which is currently being synthesized. So let's remember the key approach, one rule at a time. If we also ask the solver to simultaneously synthesize the semantics for the child terms while it is trying to synthesize that of the parent term, it will become too hard for them. So how do we get the semantics of the child terms, or at least a good and useful approximation to them, without actually solving for them? The answer is we use the examples again. The example terms and inputs will serve as a good approximation for child behaviors, and that is like what we've done with the interpreters in the whole process. And why do we do such an approximation here? That's because the examples will characterize the behavior of child terms, and if we've got all the possible input and output example pairs, that would serve as a useful and approximation for synthesizing the semantics of the parent term. And the intuition here is that even if a child's exact semantics is unknown, such an approximation would provide enough information for you to synthesize the semantics of the parent term. So let's just come through a concrete example on how we approximate the child terms semantics. Suppose that we've already got some child examples here, and we've also got the example input for the parent term, which is randomly generated. And we're going to synthesize the semantic rule of the plus sign. We use the examples here that is already available to us to approximate the child behaviors and synthesize the following functions to fill in the holes. However, this one is incorrect. We can all tell that the O here should not be equal to O2, but O1 plus O2 instead. Soon we notice that the reason for such a mistake is that the child's examples are not enough. Here we only have the behaviors of all these child terms when their input is 1 or 2, but not when their input is 3. So essentially, we don't know the behavior of the child term X when it gets the 3 as the input. That means O2 is not constrained at all. So the synthesizer treats it as a free variable, and a free variable can equal to any value, it just creates something wrong as a result. So how about adding the lacking inputs to the child examples? We just utilize the current data flow, which is I1 equals to I and I2 equals to I, to propagate the I equals to 3 inwards to each of the child terms example set. Now that we have the child behaviors when input is 3, we will try to synthesize again. This time, given the behavior of children on I equals to 3, we generated the correct semantics here. Let's do a recap on the example to know what we've done with a flowchart. We first generate the candidates F, G, and H, then propagate the inputs for child terms, and last we get the outputs for children using the interpreter. And we iterate again and again until we reach at the fixed point. The third example is about a recursive call. Overall, the problem looks very similar to the previous one. However, recursion itself brings another problem. How should we evaluate the self-recursive call? Fortunately, they can still be approximated with examples, but when should we evaluate it? We can't always evaluate. That will lead to infinite execution. The execution of the recursion here is governed by the recursion predicate, another function we introduce to control the recursion calls. The expected results are listed below. And when the recursion predicate evaluates to false, the recursion will not be executed. And for this case, we synthesize a different output function f prime. So in the previous slide, we introduced how we approximate child semantics and how we handle the recursive semantics. Then we will come to the implementation and evaluation. For the solving of Cygos and the SMT problems, we use the CVC5. And for overall algorithm, we implemented it in Scala. The benchmarks are from two sources, the SimGUS dataset and the previous work by Kalita. The SimGUS is a framework for program synthesis, and it enables the user to specify semantics of target language while generating new programs, and to test our synthesizer To test the synthesizer, there's a benchmark set with all those problems and the semantics. To test our tool, we remove the semantics and use our tool to synthesize the semantics again. And we compare what we synthesized with the ground truth. The table here answers the first research question, the effectiveness of our tool. We try to synthesize the semantics of IMP, BV simple, which is big vector operations, and regular expressions. They all terminated within 20 minutes with the correct answers. Thus, we can conclude that our tool is effective on synthesizing semantics of non-trivial languages. And the second research question here is, how does the synthesized semantics compare to manually written ones? So for all but one languages, the synthesized semantics are the same. So there are two possible reasons for the exception. One, the algorithm is wrong, or there are issues with the semantics. In order to understand what's the reason here, we try to investigate the semantics. So the regex grammar, is the exception where the synthesized results differ. And we start by looking at the signature for semantics functions. The input of the function is regular expressions and a string of n characters. The output is a bunch of bool variables that shows what happens for every substring. By comparing the generated semantics and the manually constructed ones, we noted that some variables always take the same value, so we changed the signature to only use one variable for all this. And that means less inputs in the new semantic signature. Thus, when we try to synthesize the semantics again on the new signature, the synthesizer was faster because fewer terms will be enumerated. So let's do a recap. The main idea of this paper is the semantics can be synthesized from interpreters, and we do it rule by rule. We successfully synthesized the semantics of non-trivial languages, and we found better version of existing semantics. So there are some of the future works we have thought about. Do you know how to solve these problems? Please don't hesitate to come up with your ideas or questions. Thank you for your attention.
Thank you for the very interesting talk. We have time for questions. Georgia first.
Thank you for the very nice talk. I have a question about the template extraction. So is this step automated, or do you assume that the user provides the
Okay,
templates?
so thank you for your question. Your question is about whether the extraction of templates is automatic or manually done by the user. And maybe we haven't made it clear here, but it is fully automatic. We just scan through the all types of derivation rules that are used in the source language, and we manually derive one of this rule template for each of the syntactical constructs.
Hi, nice talk. Can you go to the slide where I started with implementation? Where
The slide of what?
The slide where the title is implementation.
The slide that's... sorry?
Which title is?
Oh, okay. Do you mean this one?
No, next.
Yeah.
Experiment.
Okay.
Yeah.
Yep.
Previous one.
Previous?
Yeah, the list of.
Oh, okay. Sorry. I'm just
Yeah.
going to...
Okay. So what I have seen from your talk, can you give me the algorithmic difference between the work you have done and the work by Kalita et al.?
Okay. So your question is about what are the parts in the implementation that is done by...
No, not implementation. The algorithmic difference. Because the way you... So the Kalita the work done by this Kalita et al., which is me actually.
I'm sorry, I can't hear you
So
clearly.
that actually, instead of doing full scale, it increments one by one, the way you do, and the way you merge things when these things doesn't work with the way you do it for child and all. So can you give me the difference from the algorithm we have implemented and what you have done? Because I couldn't get that one. It looks same to me.
Oh. Okay, so our work is different in several perspectives. The first is they are working on attribute grammars, but we are working on big step semantics. We are having a different objective of the synthesis. And the previous work by Kalita cannot characterize some of the semantic relations like the while loops, but our work can't do that. And we also we actually looked through all the benchmarks they used in their paper, and we found that most of their target languages are fully functional, but we use some imperative languages like AMP. So speaking of the expressiveness, we have much more expressiveness than their work.
Nope. And that's all time we have, so the rest goes offline. Let's thank the speaker.